Dear students, next we look on distributed tracing, a crucial method for monitoring complex systems composed of microservices. This technology enables us to observe and manage the interactions within these systems and monitor their behaviors. Microservice architecture breaks down a software system into smaller, independent services, each performing specific operations. These services communicate through light APIs and can be deployed independently across various environments. They can be spread out across different locations and managed by various teams. Let's take a moment to think about monolithic systems, which is the traditional way of building software. In a monolithic architecture, all the components of the application, like the user interface, server-side logic, and database operations, are bundled together into a single package. It's like a big machine where every part is connected and dependent on each other. This setup works well for smaller applications, or when things are straightforward. It makes the development process easier since everything is in one place, and there are fewer moving parts to worry about. However, as the application grows in size and complexity, updating or scaling just one part can require redeploying the entire system. This can slow down development and make the system harder to manage. This is how microservice systems may be structured, as shown in this example. Each block or box you see here represents a different service, each responsible for handling a specific part of our application. This contrasts with the monolithic system we discussed earlier, where everything is intertwined. In this diagram, you can see multiple services such as the web front-end, different back-end services like Service 1, Service 2, and so on, all the way up to Service 11 and multiple databases. This setup is spread across different servers, which could even be in different regions, managed by various teams. For instance, you treat these separate services as user handling, payment processing, order management, and so on. Each of these services can be developed, deployed, and scaled independently. This means if we need to update the payment service, we can do so without having to touch the rest of the system. This independence helps improve the system's resilience and flexibility, making it easier to manage and evolve. So why is monitoring so important in microservice-based systems? Let's consider the nature of these systems. Unlike traditional monolithic architectures where components are tightly integrated, microservices are a collection of independent services. In the real world, any of these services can encounter issues such as programming errors, network connectivity disruptions, hardware malfunctions, or even improper service interactions. Such issues can cause individual service failures, lead to cascading failures across services, disrupt user requests, and ultimately degrade the performance and reliability of the entire application. But with so many independent services along with various user requests, how do we diagnose and pinpoint exactly which service or interaction is causing a problem? This is where effective monitoring comes into play. Monitoring offers the observability to software systems. Based on Wikipedia, in control theory, observability is a measure how well internal states of a system can be inferred from knowledge of its external outputs. The observability and controllability of a system are mathematical duals, meaning that more observability, more controllability over a system. To be simple, monitoring refers to, can you understand what's happening inside your system? 3 foundational pillars of monitoring of a microservice-based system are trace, metrics, and logs. They together called monitoring data or telemetry data, offering comprehensive observability to microservice-based system. Starting with traces, which are crucial for tracking the journey of individual requests across multiple services. Traces help us understand the path of user requests. This is especially useful for diagnosing problems that affect user requests directly. Metrics, which are aggregate data across the system to give us an overview of its performance over time. Metrics monitor various resources such as CPU usage, memory load, and network traffic. This aggregated data helps us detect patterns or anomalies over time, making it easier to spot potential issues before they escalate. Logs record discrete events within the system. These can range from detailed operational data, like a service's internal operations, to error logs that help in pinpointing the exact moment something went wrong. Logs are indispensable for detailed forensic analysis after an incident and for routine debugging by developers. This is an example how a trace can look like. In this diagram, let's imagine a user makes a request from a web browser. This request first reaches service A. From there, it is directed to service B and service C. Service C further communicates with service D, completing the request's path through the system. This entire journey, from the web browser through services A, B, C, and D, constitutes what we refer to as a trace in this system. With this trace-based monitoring, each transition from one service to the next is captured. At each of these services, A, B, C, and D, the request's interaction is recorded as a span. So in our monitoring systems, these are referred to as span A, span B, span C, and span D, respectively. Each span provides detailed insights into the processing at each service, such as service call path, timing, success, or failure of the request, and more. This slide visually explains the relationship between traces, logs, and metrics within a microservice-based system, emphasizing how they are generated and interact over time. We take our previous example UserQuest with its trace here. Let's see how this works. The right top diagram shows that logs are generated by executing specific services in spans at certain time points. You can see that logs are depicted here as points along the timeline for each span. They help us piece together the what and when of events within our system, offering detailed insights into the operations and interactions occurring at each step. Moving to the right bottom diagram, we observe the performance metrics over time. This includes data on CPU usage, memory consumption, and I/O operations, depicted as different colored lines. These metrics are crucial for understanding the how well the system is performing, how resources are being utilized, and how responsive the system is during different stages of the user request. Together with traces, we can capture the system-level metric distribution that occurs over time during a trace, providing insights into resource impacts associated with operations within this trace. Thus, traces, logs, and metrics complement each other, forming a comprehensive observability to monitor microservice-based system over time. A common practice in system monitoring is the use of OpenTelemetry. OpenTelemetry provides a unified framework for capturing, managing, and analyzing telemetry data, including metrics, logs, and traces. As an open-source solution, OpenTelemetry allows for community-driven enhancements and support. By standardizing how we collect telemetry data, OpenTelemetry simplifies the integration process with existing systems, reduces the learning curve for new team members, and decreases the complexity of managing multiple monitoring tools. Adopting OpenTelemetry involves integrating its APIs and SDKs into our software, which is supported by documentation and community resources. This ease of integration is why it has become a popular choice for system monitoring. This slide provides a comprehensive view of the OpenTelemetry collection process, demonstrating how telemetry data flows from source to collection. The process begins with the application itself, where OpenTelemetry instrumentation is applied. This is depicted at the top of our diagram. Instrumentation can be both automatic and manual, enabling detailed collection of monitoring data, logs, traces, and metrics from the application operations. From the application, these three primary types of telemetry data are generated. Once data is collected, it moves to the OpenTelemetry collector. This component aggregates, processes, and enriches the telemetry data before sending it onward. It ensures the data is consistent for further analysis. Within the collector, an enrichment processor enhances the data, adding context and additional insights, which is then prepared for export by the exporter. This stage is essential for correlating the different types of telemetry data. The processed data is output as correlated telemetry. Here, logs, traces, and metrics are interconnected, providing a multidimensional view of application behavior. APM tools nowadays provide visual observability on OpenTelemetry data of software systems. They provide real-time data that enable engineers to quickly detect, diagnose, and resolve issues as they arise. This real-time capability ensures that application performance issues can be addressed before they impact the user experience significantly. Distributed tracing tools is one type of APM tools specifically for tracking and visualizing traces across distributed systems like microservice-based systems where applications span multiple services and infrastructure components. By visualizing how requests traverse these complex systems, distributed tracing tools help identify bottlenecks, failures, and performance issues. Jaeger and Skywalking are two popular open-source distributed tracing tools that support OpenTelemetry. Here's a screenshot of the Jaeger UI, where you can see the detailed tracing of HTTP GET requests. Each line represents a different microservice involved in the HTTP GET request. The Elastic Stack, commonly known as the ELK stack, which is one of the popular toolkit for log-related APM. Elasticsearch is the heart of the stack, functioning as a search and analytics engine. Logstash is used for log ingestion, processing, and enrichment, making sure data is optimally formatted and enriched before it hits storage. Kibana serves as the visualization layer, allowing users to create real-time dashboards that showcase insights derived from the data. The Elastic Stack, ELK stack, does support OpenTelemetry. Another type of APM tools are those which specifically for tracking and visualizing performance metrics over time in running software systems. These APM tools are for any software operation, providing continuous insight into the system's performance over time. They specialize in collecting and analyzing time series metric data, which includes any data that records how system metrics change over time. Grafana and Prometheus are two popular example tools provide such functions. Grafana has powerful dashboarding capabilities, which allow for detailed visualization of metrics. As shown in the image on this slide, Grafana provides a rich interface to create dynamic dashboards that display real-time insights into your system's operations. Prometheus complements Grafana by serving as the data source that collects and stores these time series metrics, making it an excellent backend for Grafana's visualizations. Both Grafana and Prometheus support OpenTelemetry,